Hello and welcome to this lecture on advanced robotics applications. And in the last class we looked at biped locomotion, where we started off looking at locomotion, and we said that locomotion is essentially a method of moving from one place to another. Okay, and there are different ways of locomotion. For example, you can use legs, you can swim, you can fly, you can roll, and these are all ways of locomotion. And we were looking at biped locomotion. We looked at quadruped and then biped and explained things like gait. Now, in this class, what we'll be doing is we'll be looking at more details of biped locomotion. That is a little bit more advanced in the sense that we have seen that when you have biped locomotion, basically you have two legs and you have a gait pattern. Now, in terms of the kinematics, what we'll see is that you actually have infinite solutions. What that means is that you can walk in infinite ways. That means you can have infinite leg trajectories. And something to note, which is very interesting, is that although we can walk in infinite ways, all of us walk in the same way. And that is because we are optimizing our energy and we have energy optimal gait. So the next question that we'll be trying to look at today is, what is energy optimal gait? How do you get optimization, or how do you perform optimization for such systems? The next, after that, we'll look at compliance. That is, if you add compliance on the biped robot, then what happens? For example, I can make a joint compliant, or I can make a link compliant. Then what happens to the energy? Okay. And after that, we'll move on to more advanced topics like, for example, when a robot is walking, how do you do the motion planning actually? Okay. So let's look at biped locomotion in more detail today. Then we'll look at some videos of biped robots which have been made and which can walk, and you'll be able to appreciate the kinematics and dynamics of such systems. So we are continuing our discussion on biped locomotion from the last class, and we said that when a system is walking, by a system here I mean a biped robot is walking, then we analyze the motion in three planes. Okay, so there are basically three planes on which we analyze the motion, and the three planes are depending on how you are looking at the system. For example, if I'm looking from the front direction, then we are saying that this is the frontal plane. Okay, that is like if you are considering a human being, then the human is operating so this is the front view of the human. Okay, so there are two hands and two legs, and when you see from the front, that's the body, then you have two legs here. Okay, so these are the two legs. Now the view in the frontal direction is basically what we call the view on the frontal plane. Okay, so this is the frontal view. So if I draw for a biped robot, then the biped robot is going to be like this. Okay, so there are joints here, knee joints, ankle joints, and in the body there is a torso here, a neck, and there is a head, and the robot has hands. Okay, that's a biped robot. Now for simplicity, we are only looking at bipedal locomotion. So what I'll do is I'll not consider the hands. We are simply looking at the hip joints. So these are the hip joints, then the knee joints, these are the knee joints, and then we have the ankle joints. Okay, this is simplifying the model. From here to here I've simplified, and I'm simplifying it further here. So in the frontal view, this is what it will look like. So if I simply say the hips are here, this is one joint, this is another joint, as the knee joint. So there is a hip joint, there's a knee joint, and there's an ankle joint. Okay, so that is what I have drawn here, simplified version. I'm ignoring the torso at the moment. So this is what we'll see from the frontal plane. Now on the side plane, when I look from the side in this direction, basically what I'll see is the side view, and which is on the sagittal plane, or this is also called the lateral plane, sometimes called the lateral plane. So what will I see from the side views? So when you're looking from the side view from here, you'll basically see this joint, and this joint. Okay, so you'll see exactly like this, and like this, if the two legs are together. Okay, so this is my front view, this is my side view. Now if you look from the top, what will you see? From the top view, if I'm not considering the torso, I'm just considering the hip, so I'm seeing from here. So I'll see a line with, so when I'm looking at the top view from here, what I'll be seeing is the hip joint, and that's my top view. Okay, so front view, top view, and side view, this is what you'll see. Okay, now if the two legs are not aligned, when you're walking, for example, when the two legs are not aligned, then one leg will be in front and one leg will be behind. Okay, that is the front leg and the rear leg. So these are terms that we're going to use. So this is my right leg and left leg, and you have front leg and a rear leg. Okay, so when you're walking. So now when the robot is walking, how do we walk? We have seen that we need to balance. Okay, I'll come to balance as we go along. So what we have seen that when you are walking, basically you need to balance, and what this means is that if I take the front view, so this is my front view, So what this means is that the robot will bend on one side, okay, and so it'll have some angle there. It'll bend on one side and bring the center of gravity, or what we call the zero moment point, on the foot on the ground. Okay, so the first thing that you do is you bend on one side. Okay, so bend on side. Okay, and in terms of biped locomotion, we call this the double support phase, DSP, double support phase. Okay, so when both the legs are on the ground, so let me define this as both legs on ground, this is called the double support phase. Okay, and in short, it's called DSP. Okay, now you bend on one side. Why do you bend on one side? To bring the center of gravity or the center of mass onto the foot on the ground. Okay, otherwise what will happen is if you try and lift your foot, you will fall. Okay, it will not be balanced. And then what do we do? So this is my double support phase. And then what we do is we take the other foot and move it forward. So if I take the side view now, this is my side view. This is one leg. Okay, this is my hip joint. Okay, and let's say this is my hip joint here. So what we are doing is we are going to take our foot forward like this. Okay, and the hip will also move forward like that. Now once you are in double support phase, this is DSP, you move the leg forward, you are in single support phase. So this is called single support phase, SSP. Okay, then you'll move again, this leg will move forward. If I draw it in red color, this is moved forward now, and this leg has come here and the other leg has gone forward like that. Okay, so the full robot has gone forward like this. So this has a trajectory like this and this has a trajectory like that, and the full body of the robot has gone forward now in single support phase. Okay, that's the red color. That's how the body moves forward. Okay, so you have a DSP, then you have an SSP, and then you have a DSP again, and then an SSP again. That's the gait. Okay, single support phase, double support phase. Now in this single support phase, the robot was bent on the left side. You can see it is this side. Now in the next, after the leg has moved forward, what will happen in the next phase? The robot will move on the other side. Okay, so I hope you understand what I'm saying. So now it will move on this side now. Okay, so the full thing will move on that side, and then the rear leg will come forward again. Okay, so it is moving from side to side in order to bring the center of mass projection onto the foot on the ground. And when it is on double support phase and it is bent, the rear leg comes forward and becomes a single support phase. Okay, that's how the body moves forward. So when we look at the gait diagram or we look at the walking biomechanics, okay, there are different phases which are there. First is the double support phase. Now in the double support phase, what is happening? Both the foot are on the ground and the robot is bending on one side. So in this figure, you can see that the robot is bent on one side. That angle is there. It's anti-clockwise. It is bent like this. Then it goes on to single support phase. What happens in single support phase? The rear leg comes forward. So this is the front view and that's the side view. So if you look at both the feet, this is the rear feet. Okay, it has bent on one side, and in single support phase, what is happening? This foot is coming forward like this. So this foot is in air now. You can see it's in air. Okay, so this trajectory it is taking is something like that. Okay, and all the while when it is in single support phase, the robot is bent on that constant angle. Okay, so this is all single support phase, and from here to here, and then it becomes double support phase again. Now in double support phase, again the robot bends on the other side now. So in the next DSP, what will happen? It will bend on that side. This case, it was bending on this side. Okay, so DSP, SSP, DSP, SSP, and it is going to bend alternately from one side to another side, and the rear leg is moving forward. Okay, so if you look at these figures, this is basically called the gait diagram or the timing diagram. So we have a DSP, SSP, and a DSP. Okay, now, so it basically means that the robot has to bend on one side, move his leg forward, the rear leg forward, and the body also moves forward, and that's how the system has locomotion, or it moves from one point to another. There is of course no turning here. Okay, so this should be very clear in terms of the DSP, SSP, DSP, SSP again. Okay, now what we are seeing is that the robot has to move. So as the robot has to move, this is the videos I had shown in the last class also, I think, in which case we have the frontal view, this is the front view, and you can see there is bent on the left side. So this is bent on the left side, and you can see that it is moving from one side to another side. It is just moving from one side to another side. Okay, and when it is on, this is fully in single support, double support, single support, double support. This one is the side view or the lateral view, you can see that the rear leg is moving forward and becoming the front leg, and the body is also moving forward. Okay, now if you combine both of them, front view and top view, then what we see is this view, in which case the robot is bending on one side, the rear leg is going forward, this is bending on the other side, the rear leg is going forward. Okay, so this is my single support face, double support face. Now let's look at what we talked about in terms of balance. We have seen that the robot has to be balanced. So what does this mean? That when it is on single support face, the robot should be balanced, otherwise it is going to fall. Okay, that's what it means. Now, how do we ensure that, or what does that mean? Or how do we get it? Very quickly, I had explained in the last class, I'll explain it very quickly here. So what that basically means is that when the robot is on one single support face, so the robot is standing on one leg here. Okay, each of the four, we are going to model this as a lump mass system. So this is the various masses which are there of the system, Mi. Now these masses are going to be subjected to the gravity force, which is mg, plus the acceleration force, which is ma or mx double dot. So each of the masses are subjected to an inertia force and the gravity force. Okay, and then we can sum all the forces. That is what is showing the sum of all the forces is equal to mg minus ma. And because this is the foot on the ground, so what is going to happen is that there will be a resultant force in this direction, which is my total F, and this will be balanced. Okay, so this is my total F, which is here, and this will be balanced by an equal and opposite reaction from the ground, or this is the contact force which is coming, and they'll be equal and they'll be opposite from Newton's third law. Okay, now what we also see is that if I draw it in another color, that this force which is acting down here and the other force, this has a distance from this point here now. So the force mg into that distance will generate a moment about this point now. Okay, so this will generate a moment, that will also generate a moment. And the moment will be equal to the force into the distance from that point. Okay, so there is a moment also acting. Now, so what we see, there are two equations, the force balance and the moment balance. And we are basically using D'Alembert's principle. This is a system which is moving, it's a dynamic system. Okay, so this is a dynamic system. This is something which is important. This is a dynamic system, okay, which means that it is moving. So what we do is we use D'Alembert's principle. Okay, and convert this dynamic system into a static system. Okay, so what we do is we apply an equal and opposite force such that this dynamic system becomes a static system, and at that instant we apply the equations of static equilibrium. Okay, so force equilibrium and moment equilibrium. Okay, that's how we are getting these two equations. So this is for the force sigma F, and this is for the sigma m. Okay, now from that what we see, force does not cause any problem, but in terms of the moment, what it basically means that if you have your foot here and there is a resultant moment which is coming about this point. Okay, suppose there's a point here and there's a resultant moment about which it is coming. What it means is that there is an unbalanced moment which is not equal to 0 there. So what it means, this robot is going to immediately fall on that side now. Okay, it's like saying that if you have a pencil standing, okay, so you can imagine this to be a small cylinder, and suppose I move it like that, and there is an unbalanced moment now. Okay, as long as the moments are balanced, the system is it will not fall. The moment an unbalanced moment comes inside, what will happen? It will start falling on that side now. Okay, so the zero moment point says that the mass balance does not cause any problem, but the moment balance, if there is an unbalanced moment in there, okay, then that is going to make the system fall in that particular direction. So what we take is the moment equation, and then we see from this equation we basically calculate the point. So if I have my ankle point here, let me draw it here, this is my ankle point. Okay, this is my let's say ankle point like this, and there is force acting here, okay, which is the total forces, Fg force, which is totally acting there. So this force into this distance here causes a moment. Okay, this is my Pz now. Okay, so that will cause a moment about the ankle point now, and there is a resultant moment also, which is this one now. Okay, there is a resultant moment which is there. So if this moment, what I mean is this Fg moment into Pz moment, which is going in this direction, okay, counteracts the total moment which is coming from the other direction, then the system is balanced. That means there is no resultant moment across the system, on the system. Okay, so one moment because of the forces, the other moment because of the moments being caused by the mass forces. So if both of these are balanced, then what we say is that the system is balanced, it will not fall. Now if it is not balanced, then the system will immediately fall. Okay, so there is a force And so this force into the distance, which will cause a moment this side, and there is a moment which is acting on the other side. So these two have to be balanced. Okay. So how do we find this distance pz? So we simply take pz is equal to the moment divided by the force. So this gives us the distance, which is pz. And we say this point has to be on the foot perimeter. So anywhere in the foot perimeter, if I draw the full robot like this, so this point has to be somewhere in there. As long as it is in there, the system will not fall. And this point is called the zero moment point. Okay, this is basically called the zero moment point of the system. So when we are saying balance, when I gave this, showed this video also, we saw that this point here, the black point which is moving, is the point which is called the zero moment point. Now this point is not a stationary point, it's moving. Why? Because it's a dynamic system. So when the system is moving, this point is also moving. Now going back to our single support phase and our double support phase. So what we are saying is that in the double support phase, here, the zero moment point has to be on the leg on the ground. Okay. So when the leg is up, when one leg is up on the SSP, that zero moment point has to be on the leg on the ground. Okay. And then when it goes to DSP, it goes from one foot to the other foot. So the zero moment point is here. Okay, as long as it is on DSP and then SSP, and on the next DSP, this zero moment point will move to the other foot now, because it is bending on the other direction now. Okay, I hope you can correlate this. So in this case, it was bent on this side, so the zero moment point is here. Okay, the zero moment point is there. Then it's on double support phase. Now it is bending on the other direction. So the zero moment point is moving from this foot to that foot. Now it has gone there now. Okay, and then it stays there, and then comes to this foot again. So the zero moment point is moving from foot to foot, and it's a dynamic system. So basically, so what we see here is that the dynamic, the zero moment point keeps moving from point to point, and as the robot is proceeding forward, the zero moment point has to be inside the foot on the ground. Okay, otherwise the robot is going to fall. And this is what we mean by balance. So when we talk about balance, we basically mean the zero moment point has to be on the foot on the ground. Now this video also showed the motion of the zero moment point. If you noticed it very carefully, then what you would notice is that so this video was interesting in the sense that you can see the motion of the zero moment point. So here you can actually see that black point. If you note, it is moving. In double support phase, it's on the foot on the ground. Single support phase, it is on the foot on the ground, and then it moves from one foot to another foot. And this region of the foot is called the foot perimeter, basically. Okay, so it has to be in the foot perimeter, otherwise it is going to fall. Okay, now let's proceed from here. And on the human foot also, what I explained in the last class is that the zero moment point starts somewhere at the heel, then it moves like that and moves to the toe. Okay, then moves to the other foot. So effectively, it doesn't go anywhere here, and it doesn't go anywhere on the small fingers also. Okay, now let us look at the kinematics. Now, in terms of kinematics, we have seen one kinematics is that the robot has to, if I draw the front view again, this is my front view. So in terms of the front view, the robot has to bend on one side. So it has to bend on one side, which will mean that the zero moment point is coming on the foot on the ground. That is known as an NP. This is an DSP. Okay. So the first thing it has to do is to bend on one side. Then the second thing it does, it moves from DSP to SSP. And in SSP, what it does, it takes the hip forward, okay, and it takes the leg, the rear leg also forward. And that's how the robot moves forward. Okay. Now, when the robot is moving forward, what we can see is that in terms of degrees of freedom of the system, okay, how many trajectories are possible? Here you can have infinite trajectories. Okay. Now here also you can have infinite trajectories. That means you can walk in different ways, that you know. Okay. Why? Because we have said that walking straight has 8 degrees of freedom. Now this 8 degrees of freedom would mean that you have it's 8 degrees of freedom, so you can have a large number of degrees of you can have large number of solutions. So if I consider this to be a serial manipulator, let me look at it this way. Okay, so on the side view or on the front view, if I say one of the legs is fixed, this is a fixed space for a manipulator. Okay, and there are 8 degrees of freedom on the manipulator, and that's the other end. This is my end effector. Okay, then this is an 8 degree of freedom system. So to have some trajectory here, how many trajectories can you have? You can have infinite solutions now. Okay, this can behave like a serial manipulator in which one of the legs is fixed on the ground. Okay, and it has infinite trajectories by which it can take. Okay, so the question comes that how would you optimize this? Optimize in terms of what? In terms of energy. So next, let's see. The first thing that we have to see is we are going to model this as a serial link manipulator. Okay, one of the foot which is on the ground is fixed onto the ground, and the other joints are moving forward with a particular trajectory. So this rear leg is moving like that and becoming a front leg. This one is the fixed base. So it's like a serial arm, and you're doing the inverse kinematics with 8 degrees of freedom system now. Okay, so now what we are saying is we are assigning our DH parameters. So the first thing that we do is to assign DH parameters. So we are assigning our DH parameters here. So first joint, second joint. So at the hip, let us go back a little bit again here. So if it is bending on this side, now let's go back to the other figure. So if it is bending on one side, it needs 1 degree of freedom. Okay, so on this figure, it is bending this side, so it needs 1 degree of freedom there. Then this is behaving like a 2-link manipulator. So it needs a 2nd degree of freedom at the ankle. 2, 3, and 4. So each leg has 4 degrees of freedom. The ankle has 2. One for bending in the frontal plane. The other is for moving the leg. You can see that leg there, just to keep it flat, right? So there is 1 more degree of freedom there. So basically what we are seeing is that what we need here is 1 degree of freedom on the frontal plane. That is this degree of freedom. Then the other 1 degree of freedom is this one. So that's 2. 3rd degree of freedom is this one. 3rd is here and 4th is there. So 0, 1, 2, 3, that means 4 degrees of freedom. And there is 4, 5, 6, 7 there, and up to 8 is there. Okay. So basically there are 8 degrees of freedom on the total system. And there are 4 per head. What is the distribution? 1 is here, 2 is here, 1 is here, and 1 is there. So 2, 1, 1, that's 4. Okay. Now in terms of the ankle, there is 1 degree of freedom this side, and there is 1 degree of freedom here. On the knee, it's very common, very easy. This is 1 degree of freedom, and on the ankle and at the hip, also there is 1 degree of freedom there. So that's 4. Okay. So first thing we do is to assign our DH parameters. Okay, that we have studied how to assign DH parameters for a serial link manipulator. It is more or less the same. We are simply assuming that one of the legs is fixed on the ground, and the other leg is the one that is moving. Okay, the other ones are like that. Okay, so this is fixed base, that is like an end effector. This is like an end effector there. So we put our DH parameter table, and then we find the total transformation matrices that you know how to do. Okay, so we define our generalized matrix, and then from the DH parameter table, we can find each of the transformation matrices, which is going to relate T08 to the last matrix. Okay, so this is what we are going to multiply and get. So I get the relation between the last frame and the 0 frame from here. Now, what are the various advanced topics or research that we are talking about in terms of biped locomotion? One is energy optimal trajectory generation for obstacle avoidance and stair climbing. So we can find the energy optimal trajectory. As I said, that we can walk in different ways. So it basically means that we can have infinite trajectories. So we have to optimize our trajectory in some way. And what do we optimize against? What is the cost function? It is energy. So we should walk such that the energy requirement is minimum. Okay, that's one. Number 2 is we have seen that our sole is soft. At the bottom of your sole, there is tissue and it is soft. So what does the soft sole effect have? What is the effect of the soft sole on energy? Okay. Then we can talk about compliance. We have seen that in the joints, we have compliance. So what is the effect of the joints on compliance? What is the effect of this soft or compliance on the joints in terms of energy now? Okay. And then we can talk about motion planning, compliance in links, things like that. Okay. Okay, so we'll see this one by one. So the first is that we want to optimize. I want to find an energy optimal trajectory. Okay. So we have seen that the robot can walk in 2 planes, that we have understood single support phase, double support phase, and how the robot moves forward. Okay, this is something we have seen. Okay. Now I want to optimize the trajectories. How many thetas are there? There are 8 thetas. Okay, theta 1 to theta 8. Okay. And we are basically using the Lagrangian Euler formulation of dynamics which you might have studied, that you can have Newton-Euler and you can have Lagrangian-Euler. Both of them are fine. And by doing Newton-Euler or Lagrangian-Euler, we can write the equation of motion. So the dynamic equation can be written in this form. Okay. So the dynamic equation consists of this three parts. This is the inertia term. So inertia into the acceleration. This is Coriolis plus centrifugal forces, and this is gravity force. Okay, so this dynamic equation of motion has three parts. One is the inertia forces, second is the Coriolis and centrifugal force, and the third is the gravity component. And that gives us the total torque on the joints. So this is a nonlinear differential equation coupled, and there will be how many torques? So there will be tau 1 to tau 8. Okay, that is the full matrix, and this is going to become the inertia matrix. This is acceleration vector, this is Coriolis centrifugal force, and that is gravity. Now something to note from here is that the total torque on the system depends on the acceleration, that is acceleration. It depends on the velocity and the position, and it depends on the position. So if the robot is moving very slowly, then this one is as good as 0, this is as good as 0. So only the static force is there, which is the gravity force. Okay, this is what, when we say static analysis, this is what we mean, the static forces only. Okay, that is gravity forces. But if it's moving fast, then we have inertia forces and Coriolis centrifugal forces. So the total work done, when the robot is moving, the hip is moving forward, the leg is moving forward. So the total work done can be found this way. So what we can do is we can divide the trajectory. Let me go back here again and explain how this optimization works. So in this case, what we do is we have a start point and we have a fixed point. So I know the step length. This is what is called the step length. Okay, so the step length is fixed, for example, and we have a step length, and this is the center of the step length. So please note the geometry very carefully. So what we have is the step length. Actually, it can be a variable, but let me just assume that this is a constant. Let me say this is L, and this length is also L. Okay, so the step length is L, and this is L by 2 now. Okay, that's the center of. So the rear leg starts from here. You know that point. You know where it is going to hit on the next ground. You know that point. So you can fit a cubic spline like this. Okay. Similarly for the hip, you can see that the hip is here and it went forward, it went there. So you can fit a cubic spline for that also. So the start points of the leg and the hip are known. Normally this is L by 2 and that is L by 4. This is the center point and that is L by 4 normally. So the hip moves less than the leg. Okay. Now what is the variable here? The variable is the height of that now. Okay, so similarly here you can have different trajectories like this. So what is changing? One is the gradients could be changing on both sides, or the height of the trajectory is changing. Okay, so this height could be a variable now. Okay, so what we do is when we're trying to optimize, what we are doing is I'm saying that the hip trajectory is constant. I'm giving it a particular height, okay, and I'm making this constant. On the leg trajectory, we'll find 2 points like this on the trajectory, and then fit a spline, okay, and then find the energy that is consumed for walking on the spline. Okay, so what we are doing is the hip trajectory, I'm keeping it fixed, so it will have a trajectory like this. So I'll keep that height fixed. Then I'm going to find 2 points. Okay, that means 2 heights actually. Fit a cubic spline like that, fix a cubic spline, and then divide this cubic spline into maybe 20 points. Okay, so I divide this into 20 points like this and this into 20 points. And for each of those points, I draw the leg position like this. Okay, now this is like, if I see this is my hip point, this is my ankle point, this is my manipulator, this is the leg, then it is like a 2 degree of freedom system. Okay, there are only 2 links, this one and this one. So there is one joint here and one joint here. Okay, so this is like a 2 degree of freedom manipulator. So when it is moving like this, the leg is also moving like that. Okay, so if you can very easily solve the inverse kinematics of this because it is 2 links only. Okay, so instead of trying to solve for 8 degree of freedom system, which is a redundant system, you will not be able to solve it. Okay, you will get infinite solutions and all kinds of things. It is much easier to solve from geometry. So from geometry, we can solve it very, very easily by simply saying that when the leg is moving forward, this is one leg, the hip is moving forward like that, and this leg is moving like this. And we are dividing, we know the start point, end point. We are dividing, what are we doing is we are finding these 2 points. Okay, we are assigning these 2 points in the optimization. Hip trajectory is fixed, and we are dividing this into 10 points, 10 or 20 points. And for each of those points, I'm doing inverse kinematics from geometry, and I'm finding the position, I'm finding those joint angles from geometry, okay, because this point will correspond to that point. So there is only one solution like this, and the other solution is this side. So I don't take this solution, I take only that solution. So geometrically, it's very easy. Now, how is the work done found? So for each of these points, what we do is, from one point to the next point, we find the incremental velocity, okay, and we find the torques that are going to that is acting to move it from one point to another point. So I can take 20 divisions, I can take 10 divisions. So it is going from one division to the next division. So there is some velocity which is there, and there is some torque which will be caused. The torques will be acting at the joints. So I integrate this, which is as good as saying that I'm finding the work done or the total energy of the system. Okay. So that is what we are doing in here in terms of optimization, or how I'm setting up the optimization problem. That the hip trajectory is fixed, and we vary the height of the leg trajectory, and then so basically I'll be finding 2 points. Okay. So what we can do here, let me go back again here and explain it clearly. So this is one leg. The leg moves forward like this. This is one leg only. So that's the other leg which is on the ground. So this leg is on the ground. Let me put it this color. Okay, this leg is on the ground. The blue leg is moving forward like this, and this is going like that. Okay, so the other leg is here. Okay, so this leg has gone forward like this. So the hip has moved from there to there. Okay, the hip has moved from there to there. Okay, so the hip has moved this much. No, okay, I've messed up the drawing. Okay, so this is my front trajectory. This leg will go forward like that, and this will move this much and come here. Okay, so what we are saying is that this hip trajectory I'm keeping fixed, and corresponding, I'm dividing this into 20 points like this. Okay, so I find 2 of these heights, fit a trajectory, then divide into 20 points, and for each of these points they correlate, right? So I can, from geometry, I can find what are those angles, and I take the motion from one joint to the other, from one point to another point, and find the total work done. I find the total work done, total torque, which is acting tau d theta dt. Okay, that's what we do. So I get the total for one trajectory, I get what is the total work done. Then what we can do is we can change these heights, h1 and h2. So once I change the height, I get one more trajectory. Then I do the same for this. Then I find large number of trajectories, and then find which one gives me the minimum energy. And you can do that by different optimization techniques. One way is you can optimize the trajectory itself. So what I explained here is that we are optimizing the trajectory itself, the leg trajectory. Okay, so I'm putting different trajectories here, and I'm optimizing it. Optimizing means minimizing the work done. So work done is minimum. The other way is, for each of this, you know what is the range of the motion of the joints. So what we know, this is one way of optimizing. The other way is, you know the range of motion of the joints. Okay, so we understand the range of motion of the joints. What that means is that I know exactly how much the leg is going to move. I know what is the range of each of the joint parameters, joint angles rather, because I know how much the joint is going to move. Okay, so this is going to move from here to here, it will move there. Okay, so this will come up and go there. So I know that it is going to move, theta 1 will move by how much, theta 2 will move by how much, what is the range of motion. So there's a theta initial and there's a theta final. So what I do is, instead of optimizing the trajectory here, I'm going to optimize the joint angles. Okay, so I know what is the range of theta 1 to theta 8. Each of this I know the range, theta initial to theta final. So what I'll do is I'll find 2 points in between. Then I'm going to put a cubic spline or a spline in there, and then find the corresponding torque. Okay, so in the previous case, I was optimizing the joint trajectory. I was rather optimizing the foot trajectory. Whereas in this case, I'm not optimizing the foot trajectory, I'm optimizing the joint trajectory at the joint level. And would they be the same? Would the answer be the same? Yes, the answer would be the same, because the torques in both cases have to be minimum, and they'll be the same answer. It'll give you the same answer. Okay. Now we basically used, you can use genetic algorithm is easier to use because you don't have to find gradient based searches. Okay. So what GA is basically doing when you're using the GA, so what the genetic algorithm is doing, it is putting different heights here, h1, h2, fitting a spline, dividing into 20 points, and then for each of those points it is finding the energy and summing it up and saying this is the energy of the trajectory. So by changing h1 and h2 randomly, it is generating a very large number of trajectories, which is effectively giving you all kinds of trajectories, and then saying this is the trajectory which is the minimum one. Now if you do that, what we find is this has been done, for example, obstacle avoidance. So there is an obstacle there. This is the foot on the ground which is fixed, and the rear foot has to go and become the front foot without hitting the obstacle. And in GA, these are some terms which are used, like population size, crossover, mutation, iteration, number of iterations, etc., etc. Now what you see is that the hip has moved like this, and the rear leg has moved up like this, come down like this, like an S curve. Okay, this is an optimal trajectory, optimal in terms of energy. Okay. And very interesting to note that if you look at the human trajectory, it is also like this. Okay. Now when you're climbing stairs, now this can be done for different obstacles, climbing stairs, other kind of applications. So this is the foot on the ground, the rear leg is moving like this and coming there and becoming the front leg. So this is a trajectory for climbing a stair. Now, so this is, you can find trajectories for different kind of walk very easily for this robot. Now, the other questions we tried to talk about was, if you're putting a soft material at the sole of your foot, because human, if you look at the sole of your foot, it's having soft material, right? There's soft tissue there. What is the effect of that? For example, if you're wearing shoes also, okay, what is the effect of your shoes? Because it is soft, it has rubber. Now there are two directions in which we move, the frontal plane and the side plane. Okay, so if we model the motion of this, or what is the effect of this, we can see that there is some bending at the sole of the foot there itself. And if I model this simply, okay, by saying that there are two forces which are acting, I'm putting a very simple model and saying that there is a force here and there is a force there, F1 and F2 is there, and the center of pressure is somewhere here. This is a very simple model considering only two forces here. Okay, so if we can do that and we can find what is the center of the force, because these two forces will be unequal, right? So what we can do is, what we can see is that if you are just considering this to be a force, one force acting here, another force acting there, and consider this to be a force distribution like this, then we can find the center of pressure and we can find the deformation also. What are we interested in? When the robot is bending on one side, what does the deformation look like? Okay, and we have put a very simple model. You can model the deflection simply by putting a very simple spring damper. Sorry, there's no damper. There's a spring K and X model, and your stiffness Y is equal to, it can be found from here. Okay, so X is the deformation that is happening, A is the area of the foot, and H is the thickness of the sole, and Y is the Young's modulus. And from here we can come here very easily and say that if there is a force and a torque acting at the, so there is a force at the, this is my ankle point, at the ankle, and there is a torque at the ankle, and if there are two forces like this, F1 and F2, then what is the deformation? Considering this very simple stiffness model only, where K is the spring. Okay, now depending on this, you can find what is the deflection or the deformation that is happening. Now, as you can guess, that if you put different material means different K, what will happen? The deformation is going to change. So this angle that is there is going to change. It will depend on the material now. So what was observed is that if you keep changing the Young's modulus, say for example 5,000, 6,000, 7,000, 8,000, 9,000, what you see is this, if the material is too soft, then what will happen is it will start vibrating like this. Okay, now what is being done here? Let me just explain that a little bit. So what is being done is, you are bending on one side, okay, and that was you're bending on one side. That's the double support face, DSP. So when you're bending on one side, what would happen is there is going to be a deformation. Okay, so there is going to be a deformation. Let's call this theta dashed. Now what you require for the zero moment point could be theta. That to obtain a zero moment point in the foot you require theta, but because this deformation has come in, you have theta plus theta dashed which has come in now. This is because of the deformation of the sole now. Okay, so what you need to do is you need to correct it, because what you need is theta, not theta plus theta dashed. Okay, so this one could be 10 degrees, this one could be 2 degrees. So in total you have ended up with 12 degrees. Now the zero moment point can go out of the foot now. Okay, so you need to make it 10. So what you do is that you bring it back to 10 now. So you convert this one, you reduce this by 2 and make it 8. So it becomes 8 plus 2, 10. So what is happening is when it is bending, you are bending it by some angle theta. It is overshooting that, okay, by some theta dashed, because there is a deformation there. Okay, and the total angle has to be theta. So you are making a correction on that theta now, and then by theta dashed. So what is happening? There is some kind of oscillation which is happening. So this is the oscillation that is shown here. So the joint angle, let me come to this again. I have moved the joint angle by 10 degrees. There is a motor there. But because it is soft, it has not moved by 10 degrees. It has moved by 12 degrees. So I need to make the correction, bring it back to 10 degrees again. So I reduce this one to 8 degrees. Now it becomes 10 degrees. Or it will become somewhere little less than 10 or little more than 10. So what is happening is there is some kind of oscillation going on. So you can see this, the oscillation that is there. So what we are doing, we want to bend it in a particular direction to maintain the zero moment point. Okay, but then because of the deformation, it is bending a little bit more than that. So we are bringing it back, and that is where the oscillations are coming. So if it is very soft, it will keep oscillating. That is expected. So you are seeing that as we are increasing the Young's modulus, the oscillation is also decreasing, and then it becomes some kind of stable. So there is a Young's modulus of the material that is required in order to be able to make it walk with soft sole. What is the advantage of that? The advantage being that if you're putting a soft sole, we see that if you're walking with no sole deformation, then the energy required is 3.2. Now if you're walking with sole deformation and no correction is 3.4, and if you're walking with sole deformation and correction, it is 3.16. So basically we're comparing this one and this one. Okay, no sole deformation is rigid case. Okay, but if you're putting a sole deformation with a correction, what is the correction? I explained that you're bending it by a particular angle. Additional bending is happening because of the softness, but then you make a correction on that. So here what we see is that there is saving in energy. That very small energy has gone down. That it required a little less energy because the joint moved a little less. Okay, again, that is expected from here. So this is my robot. We bent it on this side by 10 degrees, and the ZMP requirement was 10 degrees, but because of the deformation it became 10 plus 2. So I reduced this to 8. Okay, now when you're reducing it to 8, it was 10 and it is 8 now, so the energy required is less because you're moving by less angle now. Okay, and that is the reason why this deformation helps. Okay, now that was one. This was a robot that was designed with compliant legs, and it can bend on one side. There is a little bit of oscillation, but then the energy requirement is a little less. Now from this we can also build robots with compliance at the joints. Now if you look at the human legs are actuated by muscles, and then these are tendons. Now these muscles and tendons have some amount of stiffness. Okay, which means that they have some kind of spring behavior, and we can keep switching the spring behavior when you're walking. For example, when you're walking, you're running, then you're jumping. It's the same legs. What is it that is changing? The stiffness of the actuator is changing. So human beings keep changing the stiffness of our joints in order to do different tasks. Now, not only human beings, even animals, it has been found that they also vary the stiffness of their joints. For example, in the case of an ostrich, it has a long tendon. Ostrich is a bird which can jump and run very fast. So it has muscles and it has a long tendon, and it can switch the stiffness of that tendon. Okay, and that is what enables it to run and jump very fast. Several robots have been tried. So this is another design of a robot. We'll show you some of them. in which case this the design was such that there was a spring added at the joint. So if you add a spring at the joint, what would happen is that so there is a motor. Okay, so the motor output, there is a spring, and then it goes to the link like this. So I'm adding some stiffness in there, and that is what essentially gives the stiffness at the joint now. Okay, now if I do that and write my dynamic equation again, additional term comes in from the spring now. This is the earlier equation, but we had an additional term because of the spring, and because of the spring, what is happening is that the dynamics is changing. Okay, and if you want to solve this equation, we again try and optimize exactly the same way, and say that if when you are walking, your step length is fixed. Okay, you can optimize the trajectory at the leg trajectory, or you can optimize the joint trajectory. Okay, both, either way will give the same answer. But here one additional component comes in, that is the spring constant. So in this particular equation, if you see, this k is a variable. This is a variable in the optimization. So now for different values of k, you will get different trajectories. That is expected. So if you look at this trajectory, this has k equal to 0. This is rigid. Now the moment k is increased, what is happening? In this case, k is all equal to 0, but for different time steps. Okay, so in this case, the time step, it means that it goes from here to here in 1 second, or 0.5 second, 1 second, t second. In all cases, k is equal to 0. That means it's a rigid case. Okay, these are the different trajectories. So what you see is that the trajectory depends on the time also. Now this is a case where for different stiffness. So if you look at k, it's equal to 0.25, 0.5, here it is 1 Newton meter per rad. And you find that the energy is actually changing. So for different trajectories, well, in this case, the time step is the same, okay, and the step length is the same. But what we are seeing is, as you are changing the stiffness of the spring at the joint, the trajectories are changing, and the amount of energy consumed is also changing. Okay, so there appears to be some kind of an optimal, and this basically is, if when we are comparing different stiffnesses, what we find is that for this stiffness, the minimum energy is obtained. Okay, so this is an interesting result in the sense that we can have springs, but then you must have optimal springs. Okay, now something, if you note, what we said is this is only one step. This is a SSP of only one step. Now from SSP, you have to go to DSP. And then from DSP, you go to SSP again of the other foot. Okay, so if this is right leg, that is left leg now. Okay, so it basically means that you have to switch your stiffness between these phases also now. And that is what makes it very difficult. For human beings, I had shown this figure some time back. Something very interesting to note is that we can run, we can walk, we can jump simply by changing the stiffness of our legs. The muscles can change its stiffness the way we want it to behave. Whereas if you put a mechanical spring like this, I've put a mechanical spring. Now the K is fixed now. You cannot have a system with a variable spring now. Okay, and that is a direction where people are looking at in terms of research, that they are trying to make joints with variable stiffness now. That means you need to make a spring in which you can vary the stiffness, and that is not very easy. Okay, now that is very interesting to note that springs do help, and that is the reason probably we have variable stiffness in our joints. And if you're looking at the different reference angles, it does vary depending on what gait you're having. So when you're walking, running, jumping, the stiffnesses all change, and this is the reference angle and joint numbers, and this is the stiffness values, okay, for different kind of motions. Okay, so this is also something which is expected, that there are different joint stiffnesses. For example, the stiffness of the ankle is different from the stiffness of the knee. Plus, the stiffness is also a variable. So the left knee and the right knee will have different stiffness now, depending on what you're trying to do. You're jumping, running, sitting down. Okay, and that is something which is extremely difficult to do in a real system, because in a mechanical system, you cannot change the stiffness very easily. Next, we looked at, next is compliant shanks. So what we said is that you can have stiffness at the joints like human beings. Okay, we have advantages. But you can also make the links compliant. For example, in this robot, I can actually replace this. This is a rigid link, so I can put a compliant link there. So I put a C section. You're aware of C sections, so it's a C section like this. So if there is a force acting there, what will happen? It'll bend. Okay, so this is going to bend. Okay. Now, what does it help? Does it help at all, or it has some advantage or disadvantage? So you can replace this with a C section. The rigid link has been made into a compliant link now, or a flexible link, and then do the kinematics. Exactly the same thing. Okay, and what is done here is that the hip trajectory is a little bit more complex, in the sense that the hip trajectory is moving in a plane like this. In the previous case, we simply said that the hip is moving like this. Okay, but in 3D, if you look at a 3D figure, the hip is actually moving in a sinusoidal fashion. So it's a sinusoid basically. Okay, but we can model it by a simple motion like this in 2D also. Now, if it's a sinusoid, then you can model this as a sinusoidal motion, or you can model this as a simple motion like this. Okay. Now, what is done here is that we are modeling the ankle trajectory using a cubic spline. Okay. So what we are doing is the ankle is being modeled as a cubic spline. This one is a sinusoid, and then we are doing an optimization. Okay. So I'll skip this. In the case of a compliant joint, it's a little bit more tricky because the inverse kinematics has a compliant link in between now. In the previous case, the joint was like this. Now in this case, the joint has become like this because there's a compliant section there now. So the inverse kinematics is a little tricky, but it can be done. And again, we write the equation of dynamics, in which case we end up with the additional term which contains a spring. So there are two equations. One equation is this for the rigid system, and this one is for the compliant section. So there is a spring there now. Okay, so let me draw it here. So the leg is like this, and there's a compliant section like this and like this now. Okay, so that's your robotic link now. Okay. So for this, the equation is this one. It's behaving like a spring. And for the other ones, it is that one. So there are two different equations, and we can solve them interactively. For example, first you solve this one, find the force acting there. Once you find the force acting there, you can find what is the deflection. Del theta is the deflection. Once you find the deflection, you go back there again. Okay, so in cyclic order, you can solve the equation and then find the energy exactly in the same place, same way. Okay, and to find the deflections, we can use finite element modeling. So at the knee joint, this much force is acting, how much deflection will be caused. This can be found by using a finite element, and then we use genetic algorithms again. So what GA does, it finds the height of the trajectory, different trajectories, and then finds which one gives the least energy. And this is some of the results which show. So these are some of the results which are there, which is showing the different trajectories. So if it is a rigid link biped, then this is the leg trajectory, okay, which is moving. And here you can see that this is moving in a sinusoidal fashion. Okay. This is the case. Now, what about the zero moment point? What happens to the zero moment point? The green one is the center of pressure, and the blue one is the zero moment point. We can see that it is vibrating a little bit. It goes like this, vibrates, that comes like this, like this, like this. There is some vibration in there. Okay. Now, in the case of compliant biped with a compliant link biped, what we see is there is a lot of vibration here. So when the zero moment point is transferring to one side, when the robot was bent like this, okay, and then now in double support phase, it has become like this, okay, and then it has bent on the other side. So when it is bending on the other side like this, there is a lot of vibrations which are coming there now, because that compliant section is there. Okay, that tends to vibrate. Now, in terms of energy, again, we find that the energy requirement is slightly less. Okay, because what happens is the spring absorbs energy and gives back the energy. Okay, this is a video which shows a rigid link. So this is a rigid link robot, the same robot. This is the integrated freedom. Straight. Comes up the leg, and leg goes forward. The robot which goes straight. So single support phase, single support, double support. On the other side.
अभी बंद करना? तो बंद कर दियो, बाहर चला जाएगा नहीं तो उसका नहीं गिलेगा। बॉडी को थोड़ा तो बाहर नहीं फिर बंद करते हैं। बंद कर दो।
Now Now this has a compliant section. This is the compliant section there. So the link is compliant. Okay. Now if you see this one, the moment it goes on levels,
बहुत ज़्यादा वाइब्रेशन हुए हैं उसमें
that is the oscillation which will show. So a single double support phase, now it comes on the other side again. So it shakes a little bit.
और क्या कंटिन्यू
So
बंद कर
this
दो
is something that is showing that you can save energy by this design, but okay, so today's class we looked at a little advanced topic of how to optimize biped locomotion. That is, in the last class we had looked at biped locomotion. Today is basically optimization. And then what is the effect of adding springs? What is the effect of putting a soft sole? What is the effect of putting a compliant link in there? Okay. And this is interesting that all this affects energy and affects the optimization process. And if we think a little bit, the biological system like our legs, we have compliance, we have stiffness, variable stiffness. So it also gives us an understanding of the design and operation of our own legs. Okay, based on this, how does it help? It helps in the design of prosthetic devices and understanding biomechanics, understanding disease, etc. So we'll stop today